All right. How are you guys? Good? Who was dancing last night? Very good. My pleasure to talk about the Lambda architecture. My name is Michael Hausenblas. I'm Chief Data Engineer at MapReduce Technologies, and been doing Lambda now for a bit more than 1.5 years, and Spark in various cases, customers, prospects, and so on. And when I looked at that, asked myself the question, how can I implement the Lambda architecture in an efficient way so that the pain on my end and customer end goes down? So it's going to be quite techy, and if you have any kind of questions, please just shoot, very interactive, so don't wait till the end. And there should be some microphone. Any? There's some microphone. Okay, let's start. So, when I looked at the Lambda architecture initially, and then Jay Krebs came up with the Kappa architecture, I thought to myself, is there maybe a pattern behind that? So I came up with this Polyglot Processing meme, obviously lifted from Polyglot Persistence, which Martin Fowler lifted from Polyglot Programming. And by that, I actually mean, if you want to, you can check out that blog post. The processing has actually turned upside down. So you now have one distributed file system layer or NoSQL store, so HDFS, for example, and you have on top of that, and this wonderful illustration here, very proud of that, somehow signals that. So you have HDFS and all these different query engines or access engines manipulate the data, but the data is there for everyone, which is kind of upside down to Polyglot Persistence. And looking at that, I would argue that both the Lambda and Kappa architecture are kind of two manifestations of this Polyglot Processing meme. Now, let's talk a bit about fault tolerance, because this is the kind of main motivation looking both from a technical side and also how we can improve ourselves. In a distributed system setup, commodity hardware and so on, we expect or assume that the hardware fails. We compensate that by software, right? Wherever you look, HDFS, HBase, Cassandra, whatever, software compensates for the hardware because the hardware will go down. We embrace failure. But what about the developer? So I would argue there's a bit of a missing link here. Let's talk about developers. Not that kind of developer, good old Bobby Table. I'm talking about when we brought the elephant to the tea party. And that's the core problem, right? Throwing it over the fence worked fine, works on my laptop, now it's your problem, right? So let's not talk about developers. We all love and admire developers. Let's talk about human fault tolerance. And to be very honest with you, this is not an IT problem. Human fault tolerance is really something you find everywhere. Absolutely everywhere, even in the remotest galaxy. And think about developers are users. They are users of your APIs. So take care of your developers. Make them human fault tolerance. And it's not only you. All the big guys have gone through that. The Whale, banks, and even Google. All of them had large-scale outages because of humans, and humans make mistakes. So I'm going to argue the Lambda architecture to the rescue. You can challenge me on that. Kappa, there are other suggestions out there how to combat that. But I'm going to make the point that the Lambda architecture has one unique feature, and that is the immutable master data set. Bit of a backdrop here. Nathan Martz initially worked at Backtype, then at Twitter, and he's doing his stealth startup now for 2.5 years. We still don't know what it is. He just told me you will like it. I believe him. He came up with things like Storm and Cascalog, ElephantDB. At some point in time, he started writing this book for Manning. And as with every book that you want to sell, you need to come up with something new. So he said, let's call the whole thing Lambda architecture. And just to be clear, people have been doing Lambda for a long time. It's really just what Nathan did there, a bit like Jesse James Garrett around 2000, coming up with Ajax, just providing the terminology, naming certain things so that we can talk about that rather than saying this thing here and that thing there. So what is Lambda? After he listed all these requirements, I'm not going to read through that, you can look that up in the slides. The main idea really is you have an immutable master data set, you never ever update any records, you always append, we're going to have a look at an example in a minute. And any kind of query, any questions that you may ask, is really a function of all the data. And there are 3 dimensions there you want to take into account on a conceptual level. That's the latency, how long does it take to run the query and then actually get an answer. Timeliness, how up to date is the query as you ingest new data. You can argue that it's a consistency issue. And the accuracy. One thing I like, what the Google guys have internally with Dremel and BlinkDB in the Spark ecosystem, that you can have approximate queries. You say, I'm cool with 95% or whatever accuracy, but I need to be able to get the answer within a second, right? Versus I need a 100% answer, but I might not know how long the query might take. So this is one of the, traditional ways of, in a box diagram level to visualize it. And what actually happens from a data flow perspective is the new data streams in, so you're always going from that side in to that side out, right? New data streams coming in, that could be a live data stream from a device, sensor, or whatever. It could be, the Twitter fire hose. It could be, by the way, Twitter, if you're listening, not cool regarding data sift. Could be you're replaying a log. It doesn't matter. It's just stream data that's coming in. And then you're splitting up the data. You're offering the data in parallel at the same time to 2 layers, the batch layer and the speed layer. Let's, for now, just look at the upper part, the batch layer. And I might even have a pointer there, which does not work. So the batch layer. The core piece here really is the immutable master data set, right? Immutable master data set means this is all your data, and you only ever append. Append. Does that sound familiar? HDFS, append? Good fit. Then you do once a day, an hour, whatever your business requires, you create views. And again, when we go through example, it might get a bit more clear what I mean with these views. These constitute your batch views. Then, at the same time, as I said, as the data lands, you offer it or you ingest it into the speed layer. You have, you're building up these real-time views, and then the main question is really just how to merge these 2 views, the batch views and the real-time views, together in order to satisfy any kind of query. Now, what we've seen here really, if you look again, what goes in here, and let's say we create the batch views once every hour. Now, the question is, how much data does the speed layer have to deal with if we create a batch view, a new batch, or batch views every hour? Any guesses?
1 hour.
Bingo! You can take as many Docker containers as you can carry. So that's what this next diagram tells you, right? What is already absorbed, which is already in there, and whatever is not absorbed, that's what the speed layer has to deal with. And that's really, way easier if like you have 10 petabytes, and if you have in the speed layer only to deal with, let's say, a terabyte, right? You can probably keep that in memory. Let's have a look at a concrete example using OpenFlight's data. I haven't implemented that one. I've implemented another one, but essentially the same idea. So you have this immutable master data set and a very simple tuple structure. Here you have the timestamp. You always want to have the timestamp, by the way. You have the airport, the flight, and the action. So we record at this point in time in Dublin, the flight EID 123 took off. Helsinki took off. Amsterdam took off. Heathrow took off, was landing. Charles de Gaulle landing. You get the idea, right? And you always ever append down here. You never ever, once it's written, it's there. You keep it around forever. You don't throw away any data. Now that's cool, but not very useful, right? If I want to know, for example, how many planes are in the air, I would need to go through, from the beginning of time. I would need to trawl through the entire 10 petabytes, for example. So that's not cool. What we want to do is create views. One simple view is, as I just said, how many are airborne. So a view is a kind of materialization for that one question, I go over that and see every plane that has taken off but not landed yet is per definition airborne. A more complex view would be the utilization of a certain airline or airport. Right? Any questions so far? Does that make sense? Appending, creating views, pretty easy, right? Now, that's nice, but at the end of the day, you want to implement the Lambda architecture. So let's have a look at how you typically do that, how you traditionally do that. As already mentioned, HDFS being a very good fit for an append-only file system, using, for example, Hive, or Pig, or cascading, or whatever, for your batch views. Typically using Kafka as a message queue in there to buffer stuff and to ingest it in parallel to both HDFS and Storm, for example, or Samza, if you're a cool kid. HBase to merge the whole things. And then, for example, if you have the requirement to satisfy SQL queries, you might want to use drill. So that's cool, but who can spot the problem with this approach? If I tell you, go ahead and implement that, what would it suck?
You have to implement the same things 2 times.
Right. So how often have you been in my talk already? Okay. Okay, good. So the problem obviously is, in terms of, think of continuous integration and testing and everything, you have business logic once up there implemented in your Hive queries and once down there in a Storm topology. So you need 2 teams, the one Java developers developing the Storm topology, the other DBAs, whatever, SQL background, doing the Hive queries. But they implement the same business logic at the end of the day, otherwise you wouldn't be able to merge that, right? It's really just a matter of the scope, the time. So that's not cool, right? Is there a better way to do that? Yeah, you wouldn't be sitting here if there wouldn't be a better way. So let's first look at other alternatives like Hummingbird, Lambda, not entirely sure where they are currently. And well, the one I would suggest you to have a closer look at, which is Spark. Now, before we go into how to do that really, let's have a bit of a look at Spark. Who of you is familiar with Spark overall? Okay, who's using it somewhere, really like in production-ish? Okay, good. So what is Spark? Spark is a unified, it has been designed as a unified compute platform. The 2 major things there really are, it is storage agnostic. It doesn't really give a shit where the data comes from. So be it, HDFS or local file system or Elasticsearch, HBase, Cassandra, whatever. Doesn't care. It just takes the data and computes it in memory. I'm gonna get to that part, what in memory really means. And offers this core abstraction of the RDDs, the resistant distributed data set. And that's already one departure, one difference to MapReduce. There you don't really have this kind of common core abstractions. And then all these modules or APIs that you see up there, Spark SQL, Spark Streaming, Machine Learning, MLlib, GraphX, and so on, are really just different sorts of ways to manipulate the RDDs, the underlying RDDs, right? So if you want to embed, for example, you port a Hive application in here, you would just use Spark SQL, and you could embed it in your Scala code, for example. Spark Streaming, again, taking RDDs, building something, we get to that dstream, that allows you to do batch-oriented micro-batching, and so on. So it's easy to develop, easy and relatively fast. And again, just to emphasize that it is really agnostic to where the data resides, where it comes from, and where it stores it. And to give you an idea, that's the good old MapReduce API. And if you look at the Spark API, MapReduce is still there, so the porting should be rather straightforward. But there are many, many more primitives that wrap up things. And if you're a cascading user or whatever, you might be familiar with things like that. It gives you a very rich API to do things rather than building the building blocks on your own using MapReduce. Then there's the question of how to execute a job in a cluster setup. Spark, to a certain extent, follows this principles, batteries included. So it comes with this standalone cluster manager, and the recent TypeSafe survey showed that majority of people, I think 60%, are actually using standalone, which is cool. In terms of security, I think Yarn is currently the best option. So if you're having strict security requirements, you probably want to use Yarn. The most flexible option is probably Mesos, and there's also EC2. So whenever the question is, you're not developing Spark application locally anymore, how to distribute it, how to execute it in a cluster, these are your 4 options. Okay? So you have the Spark driver. That's actually that's why it's called driver, driving the entire program, that through the master, and then that depends on which cluster manager you're using, distributes the workload throughout the workers, and the executors actually then do the legwork. Now, as I said, the main achievement, both from the academic side and whatever API you're looking at, that Spark introduces are these RDDs. And here the idea, I'm not going to bore you with the details, encourage you to read that paper, that 14 pages really nicely explains everything. The main idea is not to do replication, but achieving fault tolerance through lineage. So you just remember how you got there. So one of these things is an RDD, and you have partitions in there, and the partitions typically quite naturally emerge. So if you're reading from HDFS, then guess what a partition is? You again? No? A block, right? Very straightforward. And then maybe, let's say you do a map, and then you filter, and then you join it with another RDD, and let's say this partition resides on node 1, 2, 3, and that node goes down. So Spark looks at that and says, oh, how do I rebuild that partition? Well, I have to do a map on that partition here, right? So if and things will go bad, it just, rather than replicating the data, it just rebuilds it based on this DAG, right? And this DAG is conceptually pretty similar to what you see in TES. The whole idea of this is that this DAG is really never executed until you do an action. So all these things that we've seen, map, filter, join, yada, yada, these are all operations that are actually, transformations that are actually really lazily evaluated. Only when you say things like collect, or first, or for each, or whatever, you trigger an action, then you tell Spark to execute the underlying DAG, right? I mentioned early on in memory, initially I think Spark had a bit of an issue in terms of the marketing problem. Oh, we are an in-memory solution. People said, okay, but what if the working set is bigger than what you can keep in the cluster memory? The good thing, or the good news is, or the bad news, is up to you. So if you're a developer, you got to think about to what extent are you keeping RDDs in memory, and to what extent are you swapping them out on disk effectively. So it's the responsibility of the developer to say, okay, I know this is a small RDD, I'm going to pin that into memory. This is a big one, I want to join these two, keep the big one, let's say, memory and disk 2, and that means, you know, the implications you see in this table. But at the end of the day, you need to know your data sets, your RDDs, to decide which ones to keep entirely in memory, partially in memory and disk, or entirely on disk. Okay? Streaming. We need that for the speed layer, right? We want to be able to implement the Lambda architecture with one system. So we obviously need to be able to do streaming. Now, because Spark Streaming builds upon the concept of the RDDs, it is, in a sense, limited because it has to work with whatever is there, and that are RDDs. So what really is happening is well, technically it's the receiver, chops up the input stream and creates so-called D streams, kind of extension of RDDs, a bunch of RDDs, and that's a micro batch. And then the normal execution, as you have it with the Spark low-level batch API, takes place. And then whatever you're doing with that, either online, you update something, in the Lambda architecture, it would obviously be writing it out to, for example, HBase or Cassandra or whatever. And that's what's really happening under the hood there. Conceptually, well, I should mention, because of this micro-batching, you really don't want to do low latency. So that's maybe one of the limitations. If you do require low latency, so roughly below a second, then probably Spark Streaming, and with that idea, Spark being your lifesaver, might not be the best choice. Limitation to keep in mind. But it's in a sense, a trade-off between how often you do the batch jobs versus how up-to-date the speed layer views are. And that's what's happening under the hood. Probably not going to go into great detail, just wanted to show you that the actual execution is a bit more complicated than the batch part. Receivers being one of the bottlenecks there, always keeping at least one core busy, and then you have this long-running task there that just chops up the input stream and prepares it for the batch part. You have two kinds of transformations in there. In the streaming case, you've got stateless transformations. They just operate on one batch at a time, don't look back in time or whatever. And then you've got stateful transformations that actually can span several of these micro batches and could do things like sliding window and so on. Quite nicely explained there on the Spark docs side. This is a bit tricky, and I ran into a number of issues, especially kind of visualizing what's going on. Because how do you actually, I mean, this is a very simple example here. You have got, so each of these pink or whatever these colors are, boxes is one micro batch, and what it says is we're going to take a window of 3 and then slide it every 2. That's nice, but that's a simple example. If you have a concrete business question or a business goal, and you're trying to translate that into code, into Scala code, for example, at least I'm having problems with visualizing that, how to do that. If anyone has any tips for that, visualization or whatever, you're more than welcome to let me know. Just to give you a bit of an idea, this is not, just to emphasize, this is not about bitching about Storm. This is really just to give you an idea in terms of high throughput and not so high, low latency. Spark streaming is really, also compared to commercial systems, really good. The biggest efforts in terms of making the whole thing fault tolerant and highly available typically go into making sure that the driver stays around, because unlike in a batch job where you fire and forget more or less, in case of the stream processing, you need to keep the driver around, because if the driver goes away, your application is done. So you need to keep the driver alive, the receivers, dstream has one receiver, you need to think about how to set up the receiver. For example, if you're using Kafka, you would probably want to have one dstream, one receiver per partition, and so on. So all these different moving parts you need to make fault tolerant, need to be monitored, restarted, whatever. Okay. Now, the last part, and I intentionally want to keep at least some 10 minutes. I don't have any time, but I think we should have enough time there. For Q&A, for discussions, I'm pretty sure that people might argue that this is not the only way to go or have further questions, but I want to point out a number of resources that help myself, customers, partners, and so on to get started. The one is the obvious from the horse's mouth. The guys, Databricks, they wrote this wonderful book, Learning Spark. It's available, and if you're serious about Spark, then you probably want to buy that. No, I don't get anything off of it. Databricks, together with O'Reilly, has this wonderful developer certification program. You can just go there, do that. At the various events, you can do the certification. So the lesson learned here is it's not enough if you read the Learning Spark book, right? So you should have some hands-on experience. You should actually do stuff with Spark in order to pass that. And then we have two advocacy sites, if you wish, that I'd like to point out in this context. One is the Lambda Architecture, and as you can see, for quite a while already, no update there. That's not because it's dying, it's because Nathan, not this Nathan, the other Nathan, Nathan Binance, and myself have a number of things. Hello? Did you just switch it off? Did I switch it off? Can you still hear me? Yes. Okay. So there are a number of articles in the queue. The idea behind this advocacy site is if you're implementing Lambda, no matter with what technology stack, what you're using there, send in a pull request. It's based on GitHub. and we're going to add that. And you can see there were already other contributors other than Nathan and myself. And we have a number of these in the queue, but sometimes the clearance or the approval chain in certain companies takes a bit longer. So I can only encourage you, if you have something, besides the components, tooling section is also interesting, but I would really want to learn more about case studies. So if you have been doing that, if you've been looking into that, considering it, please consider sharing it with us, with the community. The more best practices we share, the more we can learn from each other. I think the better we get at that, right? The other one is Spark-related side. Low frequency, maybe 1-2 posts per month. But again, something, if you don't want to follow the mailing lists or whatever, just want to keep up to date, might want to subscribe to that. Yes, I'm a vendor, so go and download the Mapper sandbox, everything out of the box. Coming to a conclusion. The basic insight here is it's not sufficient to scale the systems. You've got to scale the people with the systems, right? So you acknowledge the fact that the hardware will fail. You know that the hardware will fail. You compensate that through software. And now let's acknowledge the fact that humans fail, and no one of us will be perfect. And there's this old joke from the 60s where a young IBM manager just screwed up and had 1 million, lost a deal with 1 million, walks up to the manager and said, "You're going to fire me?" And he said, "No, I just invested 1 million in your education." And that's the point. It's really about, we will fail, so let's see if we find some architectural guidance, and my suggestion would be the Lambda architecture. And from there, it's just a matter of how you do and how you implement the Lambda architecture. At the end of the day, we want to have a happy elephant and a cool guy. I really like that guy. That's incredible. So my main argument would be, acknowledge the fact that people will make mistakes. There's no way around that. How can you accommodate that? How can you compensate for that? Lambda architecture, there are others, no doubt about that. And if you're considering Lambda architecture as one answer or the answer to this human fault tolerance, then the question is how to implement it efficiently. And I hope that I made the point that Spark it is. I have one more announcement. Marketing asked me to do that. We have free Hadoop training. Go there, you get an expert. And that's really it. Q&A. Do we have a microphone now? Oh yeah, perfect. First question over there. Thank you. That's really horrible.
For your view layer, what you decided to use, what you end up implementing a lot for your view layer?
Okay, so the question was, what do we use for the view layer? Was that the question?
Yeah, basically, you've seen HDFS on the left-hand side and stuff like that. In your experience, what you have seen a lot do?
Almost there. I left that clicker. Almost there. No. So let's get rid of that. Okay. So your question is what we're using here?
Actually, more the middle and, well, basically, which drives the right-hand side. So when you're aggregating things down from below from Spark streaming, where do you dump all that stuff from your experience? I know you're MapR, you love HBase, but what have you seen other people do?
I'm still unsure if I understand your question. Do you mean if we look at concrete?
Right. I mean, you use HDFS up there, use Kafka on the left, Storm down below, Hive on top, HBase, blah, blah, blah. That's that's one model.
Yeah.
If you end up using Spark,
right.
Spark streaming down below.
Very good point. I removed that one slide that actually shows.
Yeah, exactly.
Yeah, wonderful. Good point. So what you would have is obviously a Hive and Storm would then be replaced by Spark.
Right.
Yeah.
And then what do you use on the right-hand side? You still want to use HBase?
Yeah. Yeah.
And
we use HBase. Others might use Cassandra or VoltDB. What is the requirement for this serving layer merge database? You want to have, imagine queries coming in here. So you want to have low latency, right? I would argue any kind of NoSQL database, if you're adventurous, maybe even a relational database, would do. But at the end of the day, you want to be able to, merge the data from both the batch and the speed layer, right? So you want to be able to keep quite some data around. So maybe a MySQL single instance might not do it. That's why, HBase, MapReduce, Cassandra, whatever. Low latency and being able to really store the entire data set. Yep. Or the views that come from the batch and the speed layer. Yeah. As long as that is, it's a matter of how big are your views, right? If your views are, remember that one example, if that's just a single answer, yeah, maybe you get away with a MySQL database. If it's more, it really depends on your views. And Nathan, I think in his book, because it's his, he uses ElephantDB. I'm not familiar with ElephantDB other than reading it from the book. Might be a good choice, I don't know. We're using HBase/MapReduce. Does that answer your question?
Yes.
Thank you. Throwing the microphone. Sorry, just wait a moment for the microphone, please.
Okay.
Sorry. Jumped to the queue. Okay.
The most interesting and complicated part of the process is the merging and merge the views.
That's one challenge, yeah.
The question is how exactly it's the best point, the best way to make it with HBase or on query layer.
So, if I understood the question correctly, is a trade-off between doing things down here or up there. So one thing to really understand is this is not a concrete system architecture. This is, in a sense, an overall guideline. Things like use an immutable master data set, have batch and stream layer, speed layer, merging them together. So at the end of the day, luckily, you still need people like me, data engineers, who sit down with the customer, say like, okay, here are my concrete data sources, here are my business requirements, and here are the SLAs, and I'm going to come up with a concrete system architecture for this use case, for this app, guided by the principles of the Lambda architecture. I can't just, that's why I don't really like that visualization. I had a long discussion with Nathan Martz around that this is sometimes misleading because people think they can take that really like it is shown here. This is actually not supposed to show in terms of wiring components. It really should visualize, how do these things play together. If you want to take one thing with you for Lambda, it has an immutable master data set that keeps all your data around, and you're creating views off of that. That's it. And the rest is really, you might be on a different stack, you might have, developers that can do Cassandra, but not HBase or whatever. The rest depends on many other things, but that's not an architecture on that level, an architectural decision. It is a decision.
The merging way depends only on end needs of representation.
I would argue that, that the merging part here, that, whatever, like Drill is a good example, or Impala, or PrestaDB, whatever you want to use there. If you have the requirements, let's say you have a BI tool, you have, Tableau or Datamere or whatever, that speaks SQL, right? So if you have HBase there, you have a problem. You need something that actually translates that SQL query into something that, gets the data out of HBase. So you're going to need something like Drill or Impala or Presto there. That's why I say it doesn't make sense to discuss that on this generic level. It really depends on what is happening, here. Who asks these questions? And that might be different roles, right? There might be your internal BI users that actually sit in front of Tableau and click, click, click. And then you might have a second role that might be a web server or whatever, Ruby on Rails or whatever, that interactively pulls data to populate a dashboard or whatever. So this is really, way beyond any Lambda discussion. It's really just the requirement is at some point in time, obviously, you need to merge the batch and the speed layer output together, the real-time views and the batch views together, in order to provide an answer that spans everything from the beginning of time to right now. Can we first, yeah.
Do you know any use cases of using Apache Droid with Spark? And if yes, then when it will fit where? In the serving layer instead of Apache Drill, or instead of Apache HBase?
You mean any concrete use cases in the sense of
Using Apache Droid.
Droid? I must I must admit I don't know Apache Droid. I know it in terms of name, but I don't really know what it does. So what does Apache Droid do?
Well, it's like distributed OLAP cube
Oh, is it
that
like
can
Kylin?
index.
Is it like Kylin? A bit like the eBay Kylin incubator?
I don't know Kylin, but
Okay.
I know that.
I mean, come on, everyone open sources a new project every week, so of course we don't know everything.
But I know that it has the capability of merging records from the batch layer and the serving layer, speed layer, sorry.
Yeah, yeah. So, I mean, the thing is, you have to ask yourself when is the Lambda architecture applicable. So you might have for certain use cases, be it more on the analytical side, more on the operational side, different requirements. So one of the questions I usually get is, what happens if I do an update, right? I just, a single update. And then people typically look at that side. And I told you initially, the data always goes in here, which means, it will take a bit of time. I mean, it will take, let's say, an hour until your new batch view, and depending on the latency down here in that path, whatever you're using, a bit, until you see that actually there. But if you have a single record that changes and you're expecting it, that was the initial discussion around timeliness and so on and so forth. So again, all I've presented here, this is not anything that you can just take one, like you see it here, and apply it. You have to ask yourself, is my use case, does whatever Lambda offers you apply to my use case? And maybe it's not the best. And I tried to point out certain limitations, especially around Spark latency, and there are others. But I would say it is so far one of the best answers I've found in terms of combating this human fault tolerance issue. Okay, can we go back first? Because you already had one question, and good that I don't know how much time we have left, but yeah, one here, and then again the gentleman. Okay. Yeah.
Is there any techniques for load balancing in terms of generation of views? For example, some synchronization techniques of this batch layer and speed layer. For example, if there are lots of data and the data in the batch layer, it is more than in the speed layer, and how to synchronize the output.
Right, that were like 20 questions, and the answer is yes, there is. So, careful. The way you asked the question makes me believe I did a poor job in explaining what's really going on. The thing is, this is not really necessary in a sense, because whatever you have here, let's for sake of simplicity just say HBase or any other low latency NoSQL database, right? That will guarantee you, if you do it right, again, if you have something that is reliable and scales really, that it will serve the data, of course, it always depends on how many concurrent users you have. I don't know. That's why I said for certain use cases, maybe it's not the best thing. And again, no one, keeps you from putting an HA proxy in front of that. Of course you can do that. But again, this is not really in scope of what I'm trying to convey here. I'm just trying to say, think about that. Think about this immutable master data set, batch and speed layer, and merge them. This is really, to a certain extent, an implementation detail. I know this is a bad line, it's an implementation detail, but this is something where a generic answer like, yes, you should use, for example, HA proxy always, doesn't make sense, because I don't know your workload. I don't know, do you have 1 or 1 million concurrent users out there? What's the access pattern and so on? I don't know. So we need to sit down and look at that in a concrete way, and then again, would derive or create a real system architecture for your use case. And in that context, I would be able to give you an answer that makes sense. I've seen that working or not so good working. But on a generic level, it's kind of, yeah, yes.
Thanks.
If that answers your question. So we have, I think, that colleague had another question, and do you still want to ask, or? I'll ask you after. Okay. Any other questions? Going once? Going twice? Okay. Well then, that's it. Thank you.